Hello guys, welcome to the physics revision. So we are going to continue from where we ended. So this is where we ended, guys, if you remember. So let's go to the next question here. So here this is question number 12, which says a positively charged sphere is moved close to an isolated bar. Okay, this is the positively charged sphere which is moved to an isolated metal bar. So this is positively charged, this is not charged. So as usual, so here there's a total number of positive and negative charges, but when they bring this with a positive, it will attract the negative this way. So and then leave this side with only positive. So one thing that I didn't mention is that this negative charge here is caused by electrons. Electrons are put this side so that it becomes negative, but this positive charge here is caused by protons. Protons are positively charged. So it doesn't seem like protons are repelled this way, then electrons are attracted. No, protons don't move. So it's just that all electrons are attracted this way by this positive. Then this side now it remains with positive, which are protons. Yeah, so that's what you should know. So this is the situation here. So when they say which diagram shows the charges induced on the bar, so you see the one that resembles this situation is this situation here. So the answer is B. We move to this one where they are saying 14. The diagram below represents a parallel circuit. Okay, so here we have 3 volts, 3 ohms, 3 ohms. So these two 3 ohms resistor are in parallel with each other. Then this is an ammeter. So what you should understand is that when current flows like here from here, this is current direction. Okay, current, so it will come on this junction. Some current will go here, okay, which we can call current 1 maybe. Then some current will continue coming here, which will be like current 2. Okay, so in other words, current 1, this original current is equal to the current that will go in there, current 1, plus the current that will go this way, current 2. This is just for the case to show you what is going on. But the question says the current through the ammeter A is, so what is the current through the ammeter? This I which will pass through the ammeter before it divides into I1 and I2. So that current, for it to be known, that current I is the total current in the entire circuit. So for us to know that current, we need to first of all find the total resistance in this situation here. So when these are in parallel, the simple way of finding total resistance, which is R total, is going to be like, we said it should be like 3 times 3, then over 3 plus 3. So this is going to be 3 times 3, which is going to be 9, over 3 plus 3, 6. So it will be like 6 into 9, it will be like 1.5 ohms. So this will be like the total resistor here. Okay, so this being the total resistor, then what we are interested in, remember, is the current through here. So the current through the ammeter here is calculated using Ohm's law, which says voltage is equal to current times resistor. Now this is the resistor will be total. In our case here, we want to use the one which is total. So now we'll make current the subject of the formula. So current will be equal to voltage divided by R resistor total. So voltage is this that I've provided us here 3. So it will be like 3 volts divided by RT total. This one we found here 1.5. So we are going to divide 3 divided by 1.5, which is going to be 2. So current will be 2 amps. So this is the current that is going to come here. Then here to divide, some will go here, some will go here. So meaning in here there will be 1 amps that will go there, and also in here there will be also 1 amps. Okay, so it will come and divide. One goes there, another one goes there. Why is it going to divide equally? Because the resistors are the same. So our answer is C here. I already indicated here. Then we'll move. This one is saying in wiring a house, a switch is always connected to the live wire. This is A, because no current flows through the neutral wire. No. B, to avoid short circuits and overheating of elements. Let's see. C, because the circuit can never be switched off if the switch is on the neutral wire. Okay. D, to make it easier to isolate any device connected in the circuit, thus making it safe. Yeah, to make it to isolate any device connected to the circuit, so that when you switch off on the live part, then the device is switched off. So the correct answer is D. Then 16, an electric appliance is rated 5,000 watts, 250 volts. A man uses this appliance for 10 hours and pays 25 kwacha for the electrical energy used. What is the cost of electrical energy per unit? So these questions, we already know that in cost of electricity is going to be equal to power used times time times unit cost. That's what I told you, which is going to be equal to power. It should be in kilowatts, as I told you. So this one divided by 1000, it will be 5. So 5 times time should be in hours. We have been provided hours there, which is 10 correctly. Then times unit cost is 25. So this is 25. So we'll just get a calculator and do the division quickly. So do like 5 times 10 times 25, which will give us that. Oh yeah, what is the cost of electric? What is the cost of electric energy? Oh, you look at the question. That's why understanding question is very important. The question is saying, what is the cost of electrical energy per unit? So they need per unit, not what we are calculating. So this is what they already said. So they're saying, and 25 for the electrical energy used. So that is the total. So here it was 25. Okay, so this person used 25 total. Then they're saying cost. So here cost we don't know. So in short, per cost we don't know here what is there. So cost, we'll just put unit cost as it is. Unit cost. So now we multiply. Here we'll have just 25 as it is. Then here 5 times 10, it will be like 50. Then here we'll add unit cost. So we want unit cost, not 50. So divide by 50 this side. Also here by 50 to know unit cost. So 50 will go. So here we'll remain with unit cost. So here it will be like 50 into 25, which is 0.5, I assume. 50. 25 divided by 50, which is 0.5. So here we're having 0.5. So that will be the price. So meaning unit cost is going to be 0.5 kwacha. This one here, or like that, which is equal to B. So guys, understanding question is very, very important in physics or in any exam or in any situation. So let's continue. Here they're saying the diagram shows a coil in a magnetic field which is part of an AC generator. So this is a coil in a magnetic field, which is part of a generator. Okay. So then they are saying, or AC generator. So here we still have AC generator. So the diagram shows a coil in a magnetic field, which is part of an AC generator. So this is south, this is north. These are the connection. This is the coil. These are magnets. Then they're saying what must be connected directly to X and Y. So in an AC generator, it is the slip rings that we connect here. So it is the slip rings. We continue. This one came in 2013 on the 16th of October. So the question reads, study the circuit diagram in figure 8.1 below. So this is the circuit diagram. We have this is a battery which is 4.0 volts. Then we have two resistors. This is 3 ohm. This is 1 ohm. Then they're saying calculate the current through the battery. So the current through the battery is the current in the circuit, in other words. So we'll use Ohm's law, which says voltage is equal to current times resistor. So to find current here, we need to find, first of all, total resistor here provided. So total resistor, which is in total resistor, total resistor is going to be, where am I now? Total resistor RT is going to be, these resistors are in series, so you just add them as they are, normal 3 plus 1, which will be equal to 4 ohms. So now here we need current, calculate the current through the battery. So we make current the subject of the formula, so current is going to be equal to voltage over R total. So voltage is already provided 4, okay, divided by R total here, it's also 4. So 4 into 4, it will be 1 amps. So current through the battery, which is also through the circuit, is going to be 1 amps. Then we move to this part B1. How long would it take a charge of 2.0 coulomb to flow through the battery? So when they say how long is time? So it's important to know this language here, all right? So here, for you to know time, and then you are given charge, and then you are told how long would it take a charge of 2.0 to flow through the current. You know, they have asked you time, then there's also charge given you. So if they have given you time and then they have given you also charge, then another thing you have calculated already, it's current. Then you look for a formula which connects these three. It says current is equal to charge over time, but they are looking for this time here. So you make time the subject of the formula. So you say over 1, so you multiply current times time, it will be like current times time equals, then 1 times charge, it will be like charge. Then what you are looking for is current, not time, not current. So divide by current, this side also by current, so that goes, you remain with time is equal to charge over current. So you are going to substitute now. You say time is going to be equal to current. You found it to be 1 previously, you coxide, then over uh, charge is 2. Charge is 2. Okay. Then current, you found it to be 1. So 1 into 2, 2. So time will be 2 now, seconds. So here you just write 2 seconds. So here they're saying how much energy would be used in moving this charge around the circuit. So remember, the formula for energies that we had yesterday that we saw. Energy can be found by energy is equal to either power times time. And then this power is also found by current times voltage. So we can substitute where there's power here, we put current times voltage, then time comes here. So this is the formula we can use if we want. So say energy is going to be equal to current times voltage times time. So current, we know that we calculated current was 1 times voltage we were provided, which is 4. So we'll come, we'll put 4 here, times time, which we have seen that it is 2. So if we multiply here, we'll have 8. So energy is in joules. So you'll put 8 joules here. We move. So this one came in 2014. So we are saying the diagram below shows two metal spheres supported on nylon strings in such a way that they touch. Okay, so they are originally neutral. A negatively charged rod is brought close to one of them as shown. Okay, so we have two metal spheres supported by nylon strings such that they touch each other. So they are touching each other. Then they are saying they are originally neutral, meaning they are not charged. Then they are saying a negatively charged rod is brought close to one of them. So this one is brought closer to one of them. Then they are saying redraw the spheres and show the distribution of charges on them. So you redraw this one here. I'm not going to redraw because of time. So now this is negative, so it will repel all the negative, they'll come here. Negative will repel, so all the negative will come here. Then this side will remain with the positive charge like that. So this is how you are supposed to redraw these ones here. Then we move. The spheres are now separated. Then the rod is removed. Draw the spheres and indicate the distribution of charges on each of them. So like they are here, when they are separated, you separate them, then you remove this. So this will remain positive, will be negative. So it is going to be like this, okay? So it will be like when you separate them, so it will be like this one, this one. This one is x and y, x, y. So this one will be negative like that, okay? Then this one will be positive like that. So this is how this is going to be. Then the spheres are made to touch again. So these spheres are made to touch again, but there is no charged rod close to them. What happens to their charges? So when they are made to touch again, so their charge are going to move. So like some electrons will move here, back here, electrons will move here, and their charges will disappear. So you say their charges will disappear. So their charges will disappear. Disappear. I don't know if this is the spelling for disappear. So that's what you say. Then we come to here, they're saying 8a, define magnetic field. So it is a region around a magnet where attraction force is experienced. So it is a region around a magnet where the magnetic force of attraction is experienced. So when you bring a metal closer to a magnet, that region where the attraction starts from, that is what we call the magnetic field. So it is a region around a magnet where the magnetic force of attraction is experienced. So B, figure 8.1, shows a soft iron bar placed in a solenoid. Okay, so we have a soft iron bar placed in a solenoid here. Okay, then they're saying B, label on the diagram the end pulse produced when the switch is closed. So here the thing is this here, because this is positive, so current will go like this. Okay, so when the switch is closed, So the current will flow from positive going like this. So here we'll label it like this. Okay. So now when we label current like that, so we are going to use the right hand grip for us to do what? To label on the diagram here the end pulse produced when the switch is closed, the pulse that we have on this, because this will become a magnet whenever current starts passing here in a coil. Then this solenoid placed inside this coil becomes a magnet or an electromagnet. So we use your hand now. Remember yesterday I said, in the other video I said, you stretch your palm, upwards like that. Where food stays, okay, it faces upward. You stretch all your fingers upward, you stretch them. So stretch them like that, then you coil them. When you coil them, the coiling of your forefingers, not the thumb, the coiling of the fingers, okay, your thumb should be pointing this way. Your thumb right now, as you are putting your palm, is pointing this way. So, because where you're putting shimmer, it is facing upward. So now that it is facing upward, now curl your fingers, okay, not excluding the thumb. When you coil them, so you find that your fingers are coiling in this way. So meaning where your thumb is pointing, that's where the north is. Okay, so this side will be north, because that's what the question is saying. Label on the diagram the end pulse when the switch is closed. So this will be north, then this will be south. So here, part 2, they're saying draw in the space below the magnetic field around, this is around the electromagnet. So we will draw the magnetic field around the magnet. There's a space here. Now they only gave it 2 marks. So that one, if it will be like that, so this is north, this is south. Then I said this is, I'll just do it roughly, guys. So this is what we are having there. Said I'll do it roughly to finish quickly. So now magnetic field move from north to south. So you label magnetic field like that. This is what they're asking you. Then here you do like also likewise like that. So you put the arrows like that to show that, so from north to south, just like that it is done. Then state 1 application of electromagnetism. So electromagnetism is used in electric bells. Also in transformers. Then they are saying why would still be unsuitable as the core of such an electromagnet. Here there's electromagnet. So steel will not be good here because steel is hard to magnetize and hard to demagnetize. So you say because steel is hard to magnetize and hard to demagnetize. Then we move. So here they're saying table 11.1 shows the values obtained in an experiment to determine how the resistance of a lamp filament varied. So here potential difference between lamp terminals V, current through lamp A. So these are the voltages, then these are the currents. Then they're saying copy and complete the table. So if they are saying we copy and complete the table, So you are going to copy this table somewhere. Okay, let me just create some space. So if you were to copy this table and complete it, like I want to just complete this table just a bit. So like you are answering this question A, like you are going to draw. So like I'm answering A. So when I'm answering like A, I'll copy this. And when they say complete, so what I'm going to do to complete this one is to see this is the voltage, this is current. So for me, meaning I'll use Ohm's law, which says voltage is equal to current times resistor. So we want to know resistor. So resistor will be made the subject of the formula. So resistor is going to be voltage over current. So we'll be getting voltage like this divided by that current to find everything here. So that's what we'll be doing. So 0.3 divided by 0.5, which will be 0.6. Then we'll continue. So we'll also say 0.95 divided by 1. It will be the same 0.15 here. 0.95. Then here we'll have 2.4 divided by 2.4 divided by 1.5. I'll have 1.6. Then 5.4 divided by 2. Five 5.4 divided by 2, I'm having 2.7. 2.7. Repeat the same process. I'll have 10 divided by 2.5. I'll have 4. So we have completed this. Oh, there's also another space here. Haven't I put on a question now? Okay. Then here they're saying plot a graph of the filament resistance against the current through it. So the graph of filament resistor. So we are plotting resistor against current. So let's see. So I'm going to plot it in here. So I'll just get the graph. So let me put this like this. So let me just insert the graph. So this side will be resistance, then this side will be, I'll put it here, it will be current. So if you come here, resistors, I've put it in ohms. So you can also put even in ohms like that. Then here you can put current in amps. So let me just squeeze this one down, maybe to eat space. So let me just put it a little bit down here, current in amps. Then what I'm going to do, I'll draw the lines, okay, even like that. Then I'll start the issue of plotting. So I'll come to check for my data, which is this. So current is from 5 to 2, 0.5 to 2. So I'll come on current. The highest value I have 2. The lowest is 0.5, so it will not be difficult for me. So I'll say, if I have a 0 here, I'll just say, okay, this is from here up to here. I'll say this is 1, then this is 2, this is 3. Now here, from here to here, it's a box 2 centimeters. So if I'll say scale, the scale that I'm using is like on the x-axis. I've said 4 centimeters represents is equal to 1 unit. Okay, this is the scale I'm using. This is 4 centimeters. I've given it 1 unit, and here the difference is also 1 unit. Here the difference is also 1 unit. Then I'll come here. For the resistor, the highest I have is 4, from 0.6 to 4. So I'll just say 1. Okay, if I say 1, 2, 3, 4, it is also going to meet. So if I say 0, 1, 2, 3, 4, it is also going to fit. So also on the y-axis, I also say the same. 4 centimeters is equal to 1 unit. Okay, so this is the scale. So meaning, having done that, I'll start plotting because I've done my job. So I'll start plotting like 0.5, 6. So 0.5, 6. So this is 0.1. 0.5 is here on the mid. So 0.6. So this one will be like 2 lines, like here. Here on these to my things, it is like to my 2 lines is 0.1. So 0.1, 0.2, 0.3, 0.4, 0.5, 0.6 here. So I'm at 0.5. I'm saying 0.5 here on the y, on the x-axis. I'm using this 0.5, this one, to with 0.6. So 0.5 is here on the middle. 0.6 is going this way. So this is 0.5. Then going this way, 0.6 is somewhere here because this is 0.5, 0.6 here. So I'll put it there. That one, if you can't understand, it's a hard one. What I'm trying is my best for you to understand. Then I'm plotting again 1, 0.95. So this one, I'll just round it off. It will be hard to plot 0.95. So this 0.9 can be rounded off to 1.0. So I'll just get a 1. A 1 from here, I'll give it to this one. Because 0.95, it will be hard to round to do. So I'll round off this to 1.0 because I'll borrow a 1 from 9, put it to 0, it becomes 1. So meaning I'll be plotting 1, 1 so that it becomes easy. So I'm plotting 1, 1 is here. Then I'll come here, I'm plotting 1.5 to 1.6. So 1.5 here, then 1.6, this is 1.5 will be here. So 1.6 will be somewhere there. Then I'm also going to plot 2, 2.2.7. So 2, 2.7. So say 2 is here, 2, 2.7. So this is 2 here, then this is 2.5, then 2.6, 2.7 should be somewhere there. Then I'm going to also plot 2.5, 4. So I'll come, 2.5 is here, 4 is here. So 2.5, 4. So I will check that this is not a straight line, it is a curve. So I'll just join a curve like that, or the points with a free hand. So don't expect me to do a right thing on a computer, okay? So, but if me I'm doing a rough thing, then you do also a rough thing in an exam, then you are killing yourself. Do the right thing. This is a computer. It's hard to do a right thing because it is also affecting. So I'm trying my level best. So yeah, you connect them like that. So that is the graph. Then you come here, they're saying, state the two factors on which the resistance of a conductor depends. So the resistance of a conductor depends on, one, it depends on the temperature, and also depends on the length of the area, cross-section area of the conductor as well. So here, where am I answering from? Let me answer it from here. This is a D. Oh, I skipped this one. So from C, from your graph, estimate the resistance of the filament when the current through it is negligible. What type of equation is this? From your graph, estimate the resistance of filament when the current flowing through it is negligible. When it is negligible, why can't you state it? So, the word negligible, what it means is, to neglect is like when the current, like, it's non-existence, when there's no current is flowing there. So what will be the resistance? Just say it is 0. Okay, so the resistance is 0. You cannot, when the current is negligible through it, so such questions are not good questions. Okay, so because when current is 0, negligible, meaning the resistor will be 0 as well. So here, if we are to say this is, I'll come and answer it from here. This is the part C. Part C. So when the current is negligible, resistor is negligible, the current is negligible, meaning the current is 0. Then you say resistor also is going to be 0 ohms. Okay, that's what it means by negligible. That I'm now using the language. I've never seen such a question before. Even in my teaching, we don't see these things, concept in our teaching in textbooks. Such concepts are not there. So I'm just now using just understanding of English, what negligible means, then to come up with the answer. I'm not even 100% sure if my answer is correct. Okay. So then when we come to D, state two factors on which resistance of a conductor depends. So the resistor can depend on, one, temperature, then two, cross-section area. Cross-section area of the conductor. It can also depend on the length of the conductor. Length of the conductor. Then we move. This one in 2015, the diagram below shows a soft iron rod placed inside a solenoid connected to a DC supply. Okay. The ends of the soft iron rod are marked X and Y. Okay, so this is positive, meaning current is going like that. Okay. Definitely this will be north. This will be south. Because when you curl your fingers of your right arm in the direction of the current, your thumb will point this way. Position your finger in this direction, your hand in this direction. Then the palm, it should face downward. Okay. Then you curl your fingers in the direction of current. Your thumb should point this way. And where the thumb points, that's where the north is. So when they say when current is switched on, which of the following occurs? So they're saying X attracts pieces of iron filings. Yeah, it can attract because it will become a magnet, this one. Okay. Then it will become a magnet, an electromagnet. Whenever this is switched, current start flowing. This soft iron inside here, soft iron rod becomes a magnet. So this sounds to be correct. Let's listen to other options. X becomes the south pole. No, it will be north. X is north. Then Y becomes the north. No, Y is south. Then Y does not attract pieces of iron filings. No. So the correct answer is A. The diagram below shows a charged polythene rod which is moved near to The diagram below shows a charged polythene rod which is moved near to the end ara of a metal sphere mounted on an insulating sphere. So the diagram below shows what? A charged polythene rod, this one here, which is moved near to end of ara of metal sphere mounted on an insulating stand. Which of the following shows the correct charge distribution on the sphere? So this one, it will be positive this side because the negative will be repelled on this side. So this is the situation which is going to be here, which means our answer is going to be B. Then we come to this one. A battery moves a charge of 6 ohms around a circuit at a constant rate in 2 seconds, in 20 seconds. What is the current flowing through the circuit? So here, if they're asking current is equal to, they have given us charge and time. So current is equal to charge over time. Then we'll substitute charge is 2 divided by time, which is 20 seconds. So we divide that. So same 2 divided by 20, which will be 0.1. Current is equal to time over charge. Yeah. Oh, sorry. This is a 60. Yeah. Where did I get the 2 then? 60. So 20 into 60, it will be what? 3. So this will be the current, which will be C. Then 16, a heater is connected to a 200 volt supply. If the heating element has a resistor of 10 ohms, how much electrical energy is supplied to the heater in 2 minutes? So they're asking for electric energy. Electric energy is equal to, we said, I, current times voltage times time. So we are told that but here we are provided resistance, no current. So this one will not work. So let's substitute current. Current can be found by voltage over resistors. So here we'll substitute. Where there's current, there will be voltage over resistor. Okay, where there's current here times voltage times time. So this formula becomes V times V. It will be V squared over R times T. So this will be the new formula now. So having this new formula, what we are going to do is to substitute. Voltage is 200. So I'll say, okay, electrical energy is equal to 200 square because of this square. Then times time is 2 minutes. So 2 minutes, you convert it in 2 seconds, it will be 120. So 120 over. Now resistor is 10. Down here you put the resistor is 10. So here you cancel quickly here. Then here you just have 1 into 12, 12. 12 times 200 squared. So we'll just say, okay, first let's say 200 squared. Okay, that is the answer. Then times what? Times 12. So it will be that 480,000. So 480,000. So here the answer will be 480,000 joules. So the answer will be what? Will be B. Then we move. Here they are saying the diagram below shows an ideal transformer which is supplied with an alternating voltage of 240 and a current of 1 amps. They are saying if the secondary current is 5 amps, what is the secondary voltage? So whenever they talk of an ideal transformer is the one which has efficiency of 100%. Whenever the efficiency is 100%, it means that power in the primary coil is equal to power in the secondary coil. Then it means that power, it is given by current in the primary times also voltage in the primary, which also is equal to current in the secondary times voltage in the secondary. So now they've given us the values. They've told us that that the diagram below shows an ideal transformer which is supplied with an alternating voltage of that. So this is the voltage here, okay? Voltage. So here voltage is this, current is that. So come and put current is 1 here times voltage is 240 equals. Then since they are saying that what is the secondary voltage, they want the voltage here, but current here it is 5. So here we'll put 5 times Vs, we don't know. So 1 times 140, 240, it will be like 240 is equal to 5 times Vs, it will be like 5 Vs. Now we want Vs, so divide by 5, we'll divide by 5, so that Vs becomes, so this cancels, so we'll divide 240, 240, 240, 240, 240 divided by 5, it will give us 48. So that will be 48 volts, which will be D. So we move. This one says figure 7.1 shows an electrical circuit containing a 12-volt power supply and a number of resistors. So this one came in 2015, 19th August. So this figure shows an electrical circuit containing a 12 power supply and a number of resistors. Okay, so this is a 12-volt. This is a resistor. These two resistors, 6 and 3, they're in parallel to each other, and then 2 ohm and the 4 ohm, they're in series with each other. Then they're saying calculate the combined resistance of the part 1, 2, and 4. So the 2 and 4, these are in series. So the combined resistor, which is R total, is going to be 2 ohms plus these 4 ohms here, direct addition, which is going to be 6 ohms. So here you put your answer as 6 ohms, 1 mark. Then you move. Here they're saying 3 and 6 ohms. So we come here, we find the 3 and 6. So here it is a product sum. So here we said total resistor will be equal to like 3 times 6 over 3 plus 6, which will be 3 times 6. It is going to give us what? It will give us 18 divided by 3 times 3 plus 2, which will be 9. So 3 plus 6, 9. So 9 into 18, it is going to be 2 there. So 2 ohms. So here total resistor will be 2 ohms. Then here they're saying calculate the reading of the ammeter above. So the reading of the ammeter here, what will be the reading? So here, the reading of the ammeter will show the current passing in this part here. Okay, so there what we are going to use is the total resistance here and then the voltage here, because these are in parallel, so they are using the same voltage. So we'll use voltage here will be the same here and here, but since we are asked here to know the current that is going to be read by this ammeter, meaning we current the one that is going to pass here is the one they are looking for. So we use the total resistor we have found here, which is 2, because here we have found 2. So we are going to use this same formula here to same. Voltage is going to be equal to current times resistor. Then current will make it the subject of the formula. It will be voltage over resistor. Then voltage, they told us that this is 12. They gave us 12. So say 12 divided by resistor we found already there. It is 2. So 2 into 12, it will be 6 amps. So current will be 6 amps there. Then we move. This came in 2016 July, all right? Then they're saying the process of removing magnetic properties from a magnet is known as demagnetization. Demagnetization. Then we continue. An electric bulb is rated 1200 watts. If the current flowing in the filament of the bulb is 5 amps, what is the resistance of the bulb? So we are told that the current is that. So power, this is power. Power has been given to be 1200 watts. Then current has been given as 5 amps. Then they're saying what is the resistance? Resistor is unknown. So we know that we need to know the formula connecting these three. We know first that power is equal to voltage times what? Current. So we haven't been given voltage here. So meaning we know voltage alone is equal to current times resistor. All right. So meaning we'll substitute here where there's voltage or put here. So say power is equal to current, or put current where there's voltage, or put this. So open brackets here, voltage, or put I R. So we'll now simplify. So I times I, it is I squared, then R. So this is the formula we are going to use. So power will make R the subject of the formula. So R will be found to be equal to power divided by current squared, which will mean that we'll say R is going to be equal to power they've given us 1200 divided by current, which is 5. So 5 squared, so it will be 1200 divided by 5 squared, 25. So we'll get our calculator quickly and then do like 1200 divided by 25, which will give us 48. So the resistor there is going to be 48 ohms, which means our answer will be that. So ohms in readings, ohms in a symbol. So here we come to this one, the diagram below. Let us read it from here. The diagram below shows a circuit with an ammeter and 2 resistors connected. So this diagram shows a circuit with an ammeter and 2 resistors connected. Then they're saying if the ammeter reading is 3 amps, what is the value of resistor R? This one here. So here, remember I told you that here the approach we use, like if this here there will be voltage, because voltage in a series differs. We call this voltage 1, then we call it this one voltage 2, because voltage in a series differs. This will have its own voltage, this one will have its voltage. But if we call this voltage supplied is just V, it means V is equal to voltage 1 plus what? voltage 2. These two, when they are added, they should give us the voltage there. But you should know that here, voltage here, like voltage here, should be found by current that is passing here times this resistor R1 here. Okay, so this R1, then here this voltage to here is equal to the current which is passing here. You know, current is the same. Current in series is the same. The current which comes here, enters here, comes out, goes there, comes back. So it is the same. So it will be I. Then let's call this resistor here just R. So we'll come and substitute. So here we'll say, okay, V is going to be equal to, here where there's V1, we'll put here I times R1. We are substituting V1 is equal to that. Then plus V2 is equal to this. So where there's V2, we'll put I and the R like that. Then we'll say V is equal to, then this is the same, so we'll factor it out as I out. Then here will remain with R1 plus this R like that. Then since we are looking for this, okay, so then we'll get rid of the I, so we'll divide by I this side, also this side by the I, the current, so that one goes. So we'll have voltage divided by I is going to be equal to, this side will remain with R1 plus what? R, like that. Then we'll make this one the subject of the formula. So this one will cross this side, it will be like V over I minus R is going to be equal to R1. Then now this one will pass this side, like R1 is going to be equal to like V over current minus R. Then we'll just substitute, like V is going to be this one here, 36, okay, over current. We were told the current passing here is 3 amps, so 3, then minus this R here, this resistor here, 8, okay. Then we'll now do that process to be easy, so we'll just say 36 divided by 3, 12, then 12 minus 8, then it will be 4. So meaning that R1 is going to be 4 ohms, which means our answer is going to be A. So we move. So here the diagram below shows a transformer. So this is a transformer. Then they're saying, assuming the transformer is 100% efficient, what is the size of the electric current in the primary coil? So these are the things we have been encountering already. When the transformer is 100% efficient, we have been saying that the power input is going to be equal to the power output, or rather power in the primary coil is going to be power in the secondary coil. Okay, these are the things we have been talking about. I hope you have not forgotten. So here power is going to be current in the primary times voltage in the primary is going to be current in the secondary times voltage in the secondary. Now the question is, what is the size of electric current in the primary coil? So it is this current in the primary coil. So to get it, we will get rid first of the voltage in the primary, also here voltage in the primary. So this and that will remain with current in the primary is going to be voltage current in the secondary times voltage in the secondary over voltage in the primary. Then we'll substitute current in the secondary is 1.5, so put 1.5 times voltage in the secondary, it's 8 over, then voltage in the primary, this one it is 240. Then evaluate this, okay, So look for the calculator, so that will say 1.5 times 8 equals divided by 240, we'll get 0 0.05, 0 0.05 amps. So that will be our answer, which will be D. Then we will move here, 25th July 2016. Figure 8.1 shows a metal bar placed inside a vertical solenoid above a small pile of iron nails. Okay, so what we are seeing is a metal bar here inside a vertical solenoid. Okay, so there's a vertical solenoid and a metal bar here. Okay, then here there's DC supply, this is positive. So now here current will be going like that. Okay, this is how it is going to be going. So if it is going to be like that, then this one will be the north pole, that one will be the south pole when this switch is closed. And when this switch is closed, if these are iron nails, so when it is closed, this will become a magnet and it will attract these iron nails. That's the scenario here. Now they're saying describe the behavior of the iron nails when the switch above is on for several seconds and then off if the metal is made from aluminium, if the metal is made from aluminium. So if the metal is made from aluminium, if this is switched on for several minutes and off, what will happen? Okay, behavior of the iron nails. Nothing will happen to the iron nails. Nothing will happen to the iron nails. Now, why am I saying so? Because aluminium is not a magnetic material. So if you are using an aluminium here, no matter, even if you close the switch and current passes here, it will not be made into a magnet. It will not have north and south here, nothing. So meaning it will not become a magnet, and because of that, nothing will happen to these. So continue just listening, you understand. So here, to iron, what will happen if the metal is made of iron? Describe the behavior of the iron nails when the switch above is on for several seconds, then off if the metal is made from iron. So if the metal is made from iron, the iron is a magnetic material. So since iron is a magnetic material, when it is closed, it will become a magnet. So immediately it is switched, the iron nails will be attracted immediately to the metal bar. And when it is switched off, they would immediately drop. So you say here, immediately, you say iron nails will immediately be attracted to the metal and also immediately be dropped after the switch is turned off. So that's what will happen. So when the switch is turned on, the iron nails will be attracted immediately. When it is turned off, they'll be also dropped immediately. If it is made of steel, steel is a hard magnetic material. So So there will be a lagging. So the iron nail will not be will be attracted but not immediately, and will fall off but not immediately. So you say the iron nails will be attracted but not immediately. And will also drop but will not drop because it will become like a permanent magnet after some time. But will not drop after the switch is turned off. So the iron nails will be attracted but not immediately, and will also and will but so let's remove this, but will not drop after the switch is turned off. Yeah, why? Because iron, I'm saying it is a hard magnetic material. So when it will be like when I'm saying the iron nails will be attracted but not immediately, it is because if this is made of steel, meaning when current passes here, it will not immediately become a magnet. No, it will take time to become a magnet, and because of that, during that period, it will be turning into a magnet. It will not attract, so they will take time for this to be attracted until it is made a magnet. That's when it will get attracted. Now, after it has been made a magnet, when this switch is turned off, this steel will still remain a magnet. So these will still remain attracted there even if it is turned off. So they will not drop. So let's let's continue. Yeah. So we come to this one here. State the difference between electric charge and electric current. So let me create space here for answering this question. Okay, this is A, B, C, right? Okay. Okay, so the space will be created here. Come back because there's plotting. So let me create another space. So let's come back now. So here they're saying state the difference between electric charge and electric current. So the difference, you can state it in so many ways. You can say electric charge is measured in coulomb, while electric current is measured in amps. Okay, so you come like 12. I created the space. Where has it gone? I created it at the wrong position then. Oh yeah, no, it's at the correct position because there are just so many questions. Huh? No, this one, it shouldn't be after this. Space should be here. Okay. So 12N, the same. electric charge is measured in Coulomb, while electric current is measured in amps or ampere, like that. That's the difference you can put there. Don't mind for other differences. Then here B, they're saying below is a table of results obtained from an experiment to determine the relationship between the voltage and the current through a metallic conductor. Okay, so this is voltage, these are the values. This is current, these are the values. Then they're saying plot a graph of voltage against the current. Then part 2, calculate the resistance of the metallic conductor. Then part 3, okay, so let's first start with B, where we are going to plot a graph of voltage against the current. So we are going to do it from here. This is the space I created. So let's try to insert the graph as usual. So we insert our graph quickly. Let's insert our graph here. So let me just expand it, because when I expand it, it becomes a little bit bigger for everyone to see somehow. Then let me just make it dark like that. Okay, then what I'm going to do in advance, I'm going to put the lines in advance. So I will have a line somewhere here. Then also, okay, let me just squeeze it a little bit there. Good. Then let me also make another one here. It is going to be here. Okay. Okay, somewhere there. Yeah. Okay, even like that, it's okay. Then we are plotting graph of voltage against current. So voltage against current, it means this side we are plotting voltage, the title voltage against current. So we can underline it like that. Then here we can put voltage, okay, in volts. Then here we can put current. These which I'm putting here, the NU marks, so don't ignore them. So current in amps. Then you come now to see how you are going to plot these. Okay, that's going on now. Okay, I want to slide the other way around. Now I can't. What is going on? Okay, so when we come to current, the lowest value we have 0, the highest is 3. So it will be simple. So this one will come and say, this is 0, then we'll say maybe 1, this one, then 2, this one, then 3, this one. So on our scale, we'll just say on like the x-axis, we'll say like 4 centimeters is equal to 1 unit. So from here it's 4 centimeters, we have given it 1 unit. Here also the difference between 1 and 2 is 1 unit. The difference also between 2 and 3 is 1 unit. So that's that. Then let me rub first these things here. This to my red ink here that disturbing me. So then we'll come back to this other part here. Voltage starts from 0. The highest is 12. So we have a lot of units here. So come here. So here it's better we say 2, 4, 6, 8, 10, 12. Yeah. But if we say 1, 2, 3, 4, 5, 6, 7, 8, 9, we will not reach 12. So it's better we say 2, 4, 6, 8, 10, 12. Maybe this is 14. It's okay. So 2, 4, 6, 8, 10, 12. So which means that on our y-axis, we are saying 2 centimeters represents what? 2 units. 2 units, meaning that from here to here it's 2. Here also the difference between 4 and 2 is 2. Also the difference between 4 and 6 is 6 and 4 is 2. Also the difference between 8 and 6 is 2. Also here the difference between 8 and 10 10 and 8 is 2. Also the difference between 12 and 10 is 2. So that's what it means, the scale like that. So now when you do like that, you start now plotting. So easy. So here you plot like 0, 0. You come here, you put it 0, 0 will be here. Then you get back to this other one here. Oh, sorry, 0.5, 2. So here you come. This is 1, so 0.5 is here, 2. It will be this point here. This is 2. Here it is 0.5. Then you come back again. Here you have 1, 4. So here it will be simple. Here is 1, 4 here. Then you come back again. Here it will be like 1.5, 6. So 1.5 is here, 6, which is here, is there. Then you come back here. You have 2, 8. So 2, 8. 2 is here, 8 is here. So it will be like that. Then you also have a 2.5, 10. So you come, 2.5 is here, 10 is somewhere there. You put like that. Then you come back again. You see that this is 3, 12. So you come, 3 is here, 12 is here. You put there. So here it shows that this is a straight line. So you are just going to, let me put a straight line like that. I'm just going to put a straight line here. So it will not be difficult from 0. The straight line must pass through all the points like that. Okay. So that is it. That is it, guys. You see? So simple. So we get back to the other question. So here we have answered, this is B1. So say this is 12B1. Then you come here. They're saying to calculate the resistance of the metallic conductor. So the resistance of the metallic conductor here will become the gradient of this. So the gradient of this, remember gradient, I told you that gradient M will be equal to y2 minus y1 over x2 minus x1. So you pick 2 points that are scattered, like this one and maybe this one. So here, this side, on this point, you come here, you find 12, which will be your y2. You pick minus, then you come on this point, you come here, your y2 will be 2 here. You put 2, then over. You come on this one, you come down, your x2 will be 3. So 3 minus, you come down here on this point, you come down here, your x. So these which I've circled here, you don't circle them on your graph. Me, I've just circling them to teach. On your graph as I don't circle them. So this one will come down here. This is 0.5. So 0.5. So you say equals, then 12 minus 2, it will be like 10 over 3 minus 0.5, it will be like 2.5. Okay. So 2.5 into 10, it is going to be how many? Is it 4? Let me just say do the division. 10 divided by 2.5 is equal to 4, yeah. So 4. So now, you are going to say 4 ohms. So you are going to say, this you are going to put it as B2. So you are going to say, therefore, resistance is going to be equal to 4 ohms, like that. Oh, let me charge this one a little bit so that we'll get back. So let's continue. This one came on the 31st of July 2017. The diagram below shows a steel magnet being withdrawn from a coil of wire in the direction shown to a point as far away as possible. Okay, we are seeing in this diagram a steel magnet moved out, okay, in that direction. Okay, so it is being moved out in that direction to a far position as possible. Then the same, what is the effect on the steel magnet due to this action? So a steel magnet is being moved far away. So if it was placed, when you check in this one, that symbol there, it means this one was an AC. So if this steel magnet is being removed from a solenoid which contained the AC, meaning it was being demagnetized. That's the thing. So when they say what is the effect of the steel magnet due to this action, it means they are saying no change, no, becomes magnetized, no, becomes demagnetized, yes, because the process of demagnetizing or removing magnetic property of a substance can involve also putting a magnet into a solenoid connected to an AC current, AC voltage or current. When you put them in a solenoid connected to the AC, then they will become demagnetized, because this diagram is saying, the diagram below shows a steel magnet being withdrawn from a coil of wire in the direction shown to a point as far away as possible. So they are removing it. Now, because of that, meaning if they are removing it, meaning it was there. Okay, so let's continue. The diagram below shows an illustration of a transformer with 100 turns on the primary coil and 225 turns on the secondary coil. Okay, so this is the same situation that we have been going through of a transformers. So in a transformer like this one, we are told that we have 100 turns on the primary coil, 100 turns, and then we are given the voltage 12 volts, and then 25 turns on the secondary coil. Then they're saying what is the voltage induced across the secondary, what will be the voltage here. So you have seen this is a circuit symbol for a transformer, so you must also remember this. So we told you that I told you that the formula will be like voltage in the primary over voltage in the secondary is equal to number of turns in the primary over number of turns in the secondary. So what they are looking for is the voltage induced in the secondary, which is the Vs. So you cross multiply to make it the subject of the formula. So these times that it will be like voltage Vs over N P is going to be equal to also these times this it will be Vp then Ns. Then you want Vs not Np, so you divide by Np also here by Np, so that this goes, you remain with Vs is going to be Vp then Ns divided by Np, then equals, so Vp voltage in the primary is 12, so 12 times Ns number of turns in the secondary is 25, okay, over Np number of turns in the primary, which is 100. Okay, so now we are going to do the evaluation using our calculator. So it will be like 12 times 25 equals divided by 100 or 3. So it will be 3. So this will be the free vote here. So the answer will be A. Then we move. This one says the diagram below shows a positively charged rod placed close to two metallic spheres A and B, which are initially neutral. Okay, so this is a positively charged rod that is placed close to two metallic spheres A and B, which are initially neutral. So if they were initially neutral, now bringing it closer, this one has become negative, this one has become positive. Now they're saying which statement is correct? A has lost positive charges to sphere B. Positive charges don't move anyway. So B gained electrons from sphere B. Yes. So electrons are the one which moves, because when this is brought closer, for it to have overall negative charge, it means the electrons which were here were attracted to this side, and then this remained with only positive charge. So this makes sense. But here when they say D, A has lost positive charges to the charged rod, no. So this C makes sense. A has gained electrons from the charged, no, gained electrons from sphere B. So it has gained electrons from sphere B. So the answer is B. Then we come to this. The diagram below shows a circuit with 4 ammeters connected at different positions and 3 resistors of different values. Which of the 4 ammeters labeled A, B, C, or D would show the largest reading? So the only ammeter that would show largest reading is the one at D, because here when current comes here, which is current coming like that, current total like that, when it comes here, some will go here. Let's call that current 1. Then the other one will continue coming here. Let's call that current 3. But that current 3 also, when we reach here, it will divide. Some will go here. Let's call that current 4. Then some will go here. Let's call that current 5. So when all of them, they'll come here. Here we'll have current 1. Here we'll have current 4, right? Here we have current 5. So all of them, when they come here, they'll add. Okay, they'll add up to, again, current, the total current that is going there. So this D is the one which will show largest reading here, D. Okay, we continue. A secretary in a manager's office uses the following appliances with respective power ratings. Okay, electric kettle 1200 watts, printer 600 watts, then a computer 100 watts. Then they're saying given that the cost of electricity is 0.80 per kilowatt hour. Calculate the cost of operating all the three appliances at once for 12 hours. So now, remember here we need to calculate cost individually. So formula for cost of using electricity, I said it is going to be power times time, then times what? Unit cost. So calculate for each. Like for the electric kettle, we'll say equals the power, we'll divide this by 1000. Okay, so if we divide like this 1200 by 1000, it will be like 1.2. 1200 by 1000, okay, it will be 1.2. So here power will be like 1.2 times time. Time should be in hours, 12 hours, right? Then times unit cost. Unit cost is 0.8. So let's do that evaluation quickly. So 12 times 0, I mean times 12, then times 0.8. So we're having like 11.52. So this one will be 11.52. That will be the cost. That is a kwacha. Then this one here, printer, also say cost again for printer alone is going to be, this one will divide by 1000 so that it becomes 0.6. So 0.6 times the same 12 times 0.8. Okay, so I'll also do the same. So 0.6 times 12 times 0.8, I'll get 5.76. So 5.76 kwacha for the printer. The computer, 100 divided by 1000, it will be 0.1. So here the cost also, cost is going to be equal to 0.1 times 12 times what? Times 0.8. So we'll do the same. 0.1 times 12 times 0.8 to get 0.96. So this one will be 0.96. Then we'll add total this plus this plus this to find the total now. So we'll say now this same one plus 5.76 plus 11.52 equals, it will be 18.24. So 18.24, which means the answer is D. We'll move. Figure B 7.1 shows magnetic field lines between the poles of two magnets. Okay, so we have these are magnetic field lines between the poles of two magnets. This is a magnet, this is a magnet. So they have not showed what the poles are, but we know the poles are. Whenever you see these magnetic fields coming out and pointing away from something, meaning this is the north. Even in this side they're coming out, meaning this side also is the north. Okay, then meaning this side is the south, this side is the south. Then this point here where there is no electric field is not called the neutral point. Neutral point. So when they say name point R, all right, so you see it's neutral point. Then B, if P is the south pole, they've told us P is south pole, which we already know. What are the poles Q and S? So Q is north. We have already said that is going to be north pole. Then T we have already said T will be south pole. South pole. Then we come here, they're saying explain how soft iron keepers help magnets retain their magnetism for longer period of time. So because they lock magnetic fields. So this is explain how by locking. So because they lock, so how they do so by locking magnetic fields so that they do not reverse. They do so by locking magnetic fields so that they do not reverse the pose. So they are what we call magnetic keepers. So magnetic keepers are placed at the end of magnets. So when they are placed at the end of magnets, the magnetic fields won't be leaking out, so it will be like locked. So when magnetic field is locked, then there will be no reversing. So when they say explain how soft iron keepers help magnets retain their magnetism for a longer period of time, you say they do so by locking magnetic fields so that they do not reverse the pose. Then D, state two differences between iron and steel as magnetic materials. So you say the first difference is that iron is easy to magnetize, while steel is hard to magnetize. Then here you say iron is used to make electromagnet, while steel is used to make permanent magnets. That's what you should know. Then we move. Here figure B8.1 shows 3 resistors connected to a 12-volt battery. So these are 3 resistors, this 2 ohm, 12 ohm, 6 ohm connected to a 12-volt battery. Then they are saying calculate the effective resistance between X and Y. So here they never indicated the point at which the effective resistance was supposed to be calculated. So I'm sure in an exam they should have decided here, between here and here. It should have been between here, maybe X here, Y here. So the effective resistance means the total resistance. So it would mean that total resistor which is effective is going to be equal to like 12 times like 6, then over like 12 plus 6. Then you do like wise, so you are going to get like 12 times 6, which is going to be 72. So 72 divided by 12 plus 6, which is going to be like 18. So like in 72, you say 72 divided by 18 is going to be 4. So this one will be like 4. So this is a 4 ohm as the effective resistor. Then we move, then they're saying the current flowing in the battery. So current flowing in the battery is current flowing in the circuit. So that current flowing in the circuit must be found by finding the total resistor first. So since here we have found that the total resistor which is there here is 4 ohms. Now these 4 ohms and these 2 ohms, they are in series. So the final total resistor in the whole circuit is going to be like 2 plus 4, which is going to be like 6 ohms. So this is the one we are going to use to find the total current passing through the circuit, okay? Because when they say the current flowing in the battery, it's more like the current flowing through the circuit. So you know you use voltage is equal to current times resistor. So this resistor will be resistor total RT, which we already found as 6 ohms. Then here we need to find current. Current is going to be voltage divided by R total now, which will be equal to voltage. Here you are seeing it is 12. So it will be like 12 divided by this R total is 6. So that 6 into 12, it will be 2. So current will be 2 amps. So here you write 2 amps. Then here they're saying the current flowing through the 6 ohm resistor. So you come here, they want the current that is passing through the 6 ohm resistor here. Now, for you to know the current that is passing along through the 6 ohm resistor, first of all, you need first of all to know the voltage here. Voltage here, you call it V1, okay? And then voltage across this parallel thing here, which we are going to call V2, like that, okay? So it is quite a tricky situation here. So, however, I've already explained this, right? So this has already been done. So we are going to do like, you know, V total current voltage is going to be V1 plus like V2, okay? So voltage here will be easy, but here not yet easy, okay? Even here it will be easy, okay? So voltage here, we know the current passing here. So I will not resort to that long formula. I will just come back to here. Voltage here, we need to know it. So voltage here will be easy because we have current passing and the total resistor is 4. So here we find voltage across, and so we are not using this one, which will be a little bit longer on your part, but it is going to work. But I want to shorten the process because I've seen that even here we can still calculate voltage. Knowing the current here, we already found the total resistor, which was 4 ohms, and we know the current that is coming here, it's 2 amps. It's the one crossing here coming this side. So here we know two things: total resistor, and also we know total current passing there. So we can know voltage. So first of all, we'll say voltage voltage is going to be equal to current times resistor. So the voltage is going to be current is the same 2 ohms plus total resistor is 4. So voltage here is going to be actually like 8 volts. So now this is voltage. So now that we know the voltage here, so here this V2 is now 8 volts. So automatically, if this is V2 is I just want to open your mind, but it is not what we are calculating. If V2 is 8, then definitely V1 here, it is like 12 minus 8, it will be like 4. In case if you want to know the voltage here, this is the simplest thing you can do to find it. But here we are interested in this voltage V2, it's this one here. So now that we know it, but the question is asking us to find the current here, because that current, when 2 amps comes here, it is the one coming out of this side here, okay? Also it is coming out this side, going that way. Now when it comes here, some is going this way, some is going that way. So how will we know that going there? So we would need to use the voltage we have found here on this point, which is 8, then with the resistor here. So we'll concentrate the resistor and that voltage 8. So we'll now say current, we know it is found by voltage over resistor, and voltage we have found that it is 8, then the resistor itself is 6, so 6. So now 8 divided by 6 is what we are going to do here. So I will say 8 divided by 6 is going to be 1.333. So it will be 1.33 amps. So that will be the current 1.33 amps. So in case they asked you to say, what about the current which will go in the 12? So you just say 2 minus 1.33. Here, what is coming this side is 1.33 amps. So you say 2 minus this, you know what went this side, okay, which will be like 0.7, I'm sure. So then we move. So this one is about plotting like the one we plotted. Let me read. Table C 2.1 shows a table C 2.1 shows a table with corresponding values of potential difference across a touch bulb and the current flowing through the same touch bulb. Using correct circuit symbol, draw a clearly labeled diagram of a circuit which would have been used to obtain this data. Okay, so let's see. Oh, there are other questions here. Okay, so let me answer it. So let me just create space here. For answering it. So we are on a C2A. So C2A, they're saying we draw a circuit diagram symbol to show how this arrangement should have been done to collect that. So there's a bulb. So here it will be like you need to have a source of power, which will be a battery, in short, some battery. So it should go like that. Okay, then you connect the ammeter. Okay, after you connect the ammeter, then you need to have, this one is the bulb. The bulb is also represented by that. Then maybe you can even put a switch here if you want, but I've not put the switch there. It's okay. Then you connect it back to there. So then here you put a voltmeter like that. This will be the voltmeter. So this is the arrangement they did. So the question says, using correct circuit symbol, draw a clearly labeled diagram of a circuit which, now, so you'll label it. So this one, battery. This one, voltmeter. This one, bulb. Then this one, ammeter. That's all. Then you come to be on the graph paper provided, and using the data in the figure above, plot a graph of the current on the x-axis and then potential difference on the y-axis. Okay, here they now specified, and then they've given you 3 marks. From the graph state whether or not the filament of the touch bulb is ohmic conductor. Explain your answer. Okay, so ohmic conductor. Okay, so let me just plot this one, except that we have plotted a lot, so we can plot as well, no problem. So we'll come to this one here. Let's just plot. I think this will be the last one I'm going to plot on this one, so that I can end this one and then look at it. Go to, I think, radioactivity and other things, because we have delayed a bit. So let me just do like that. Let me draw in advance the lines. So it will pass through here. Let's leave it like that. And this one. Okay, yeah. So this side will have voltage in volts, then this side will be current in amps. Then we'll come back to look at it, or we'll put the title first. So this is voltage against current. Then we'll look at the data provided. So on voltage, the lowest is 0.2, the highest is 40. So this, guys, is going to be hard on our part. Where we have the lowest like this, then the highest like that, this is going to be hard. I'm not going to lie. Then this one, current 0.423, this will be easy, but this one is going to be hard. So I'm just praying to see how I'm going to make it. So here we'll just do 0, 1, 2, 3, 4. So like the scale, it will be easy on the x part. So the scale will be like on the x-axis, we are saying 4 centimeters is equal to 1 unit. Now where it is hard, it is here where we are running from 0 to 40. So meaning we should do like 10, 20, 30, 40, or let's say 10, 20, 30, 40. Yeah, so we'll have like 0. This is 10, 20, 30, 40. So it is quite hard. So this one on the y-axis, we are saying 4 centimeters represents 10 units. From here to here, it's 10. Now, you'll see why it is going to be hard, because to locate 0.2 here, it's going to be quite hard. So if this is maybe 1, 2, 3, 4, 5, 6, 7. Okay, say 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, so now here we are having like 1. So such a graph is going to be hard. Using this graph I needed a big one, like I'm doing not on the computer, like I'm doing in reality, to use the full graph paper. But this one, you saw it, I reduced a graph paper so that I expand it a little bit, it looks bigger. But now like this, to come and locate this value, 0.2 will not be located here. I will not manage to locate a 0.2 because on my graph I am only able to locate 0. I'm only able to locate 0.1. Like this is 0.1. After 2 small lines is 0.1. It is like 0. This one is 0. 2 point is like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm only able to locate like 1, 1, 1. I'm not able to locate the 0. So for me, I'm going to ignore this because I can't locate it unless if I was using a real graph and I'm not on the computer, I'm using the bigger graph. Maybe I can manage to work on that, but not like it is on the computer. I can't locate this, so I'll ignore this part. This part myself, I'm not plotting it. I'm starting from here. From here, I can locate 1 here. So 1 is here. So from here to 2 small boxes, I will locate 1. So I've ignored the first one. I've come to this one. So I'm plotting 0.8 comma 1. So 0.8, it's able to be located. So this is 1. So these boxes are like, let me first do like this. First, let me do like this. Did I change this one to this dark one? Okay. Okay, this one at least. And let's see if I use this one. Okay, I think to me this one is much better. Yeah, so I'm able to know that 0.8, like two boxes, like this is 1, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8. So 0.8 comma 1, for me, I'm locating it here. So people who do this, they just guesswork. They just don't mind how hard it is going to be to plot these values here. So what we have plotted previously, Oku, it was simple. Those were good examiners. But this one, who said this one is not a good examiner, you are going to see that plotting will be hard. So you come here. The next one we are plotting is this one here. 1.2 comma 5. 1.2. 1.2. So this is 1.1. 1.2 comma 5. 5 is this line here. So 1.1, 1.2 comma 5. This will be the 5. Then yeah, then 1.6 comma 10. So 1.6. So 1, this is 1.5, 1.6 comma 10 there. Then coming back, then 2 comma 16. So 2 is here. So this will be like 15. Then 16 will be like there. Then 2.4 comma 23. 2.4. This is, if this is 2.5, 2.4 should be here too. Okay. 2.1, 0.2, 0.3, 0.4. Okay, 0.4 comma 23. This is 20, 20, 21, 22, 23. This is 20, 21, 22, 23. So there. Then here 2.8 comma 31. 2.8. So this is 0.5, 0.6, 0.7, 0.8 comma 31. Comma 31 is here. So this is 0.5. 31 is here. 30.5, 0.6, 0.7, 0.8. So 31 will be here. Then, oh, that's not 31. Um, 6, 7, 8. 31 will be this point here. Yeah, 31. Then 3.2 comma 40. 3.2. 3.1.2 comma 40. So 40 is here. 0.1, 0.2 there. So this is not a straight line. So that other point which I missed, I don't know, maybe we are going to be here, but I'm not going to show it. I'll just connect this one. So this one is not going to be a straight line graph, as you can see. So you try your level best to draw it nicely. Here you are not using a ruler. So now I've missed here. It doesn't mean that you miss. I've just failed. So you have to join them nicely. They meet all the points. I've just failed because I'm operating on a computer. So we move. Here they're saying from the from the from the graph state whether or not the filament of the touch bulb is an ohmic conductor. So this is C. So this graph is not a straight line. So since it is not a straight line, or here, since it is not a straight line graph, then we are going to say it's not an ohmic conductor. So this is the 2 what? This is the C2C. So going to answer C2C. You are saying this is not an ohmic conductor because the graph is not a straight line. So if the graph is not a straight line, then it is not an ohmic conductor. Then we come back to this other one, which is the D1. Okay, so we have D1. They're saying use the graph you have drawn to determine the value of the potential difference across the touch bulb when the current flowing through it is 2.6 amps. So when we come here, 6.2, if the current is 6.2, 6.1 point, oh, sorry, 2.6, 2.6, so 2.1, oh, this is 2.5, so 2.6 is here. So this is 2.5, 2.6 is here. So when we draw a line from down here, passing through this, you draw a straight line. Okay, using a ruler, you use your ruler, you draw here, but 2.6, a straight line, a dotted one, in fact. So when it touches the graph here, then where it touches the graph again, you draw another dotted line straight like that. Mine is not straight, so where it touches, like if this is 20, this should be 25, then that should be 26. So there you are going to find that here the voltage is going to be 26 volts when current is equal to 2.6 amps. Then here part 2 they're saying calculate the resistance of the touch bulb when the current through it is this. So resistance, now we have found the voltage. So part 2 will make the resistance the subject of the formula. Resistance is equal to voltage over current. So we found that their voltage was 26 divided by current 2.6. So just use this one, like 26 divided by 2.6, which will give us 10. So the resistor will be 10 ohms. Okay, so let me see, with electricity and magnetism and all that, I think let me end here. Let me start preparing for electronics, then atomic physics and radioactivity. Okay, looking at time has really gone. So, and I have so many slides that are remaining, but these slides which are remaining here, if I aim to finish them, I am at 77 out of 56. All these questions that are remaining here, all these questions which are remaining here, at least what I've solved already, I think is making sense. Maybe let me try to solve these, which are few. I'll be quick, maybe these, they'll help someone, maybe. So let's come to this one. It came in 2018. A bar magnet was broken into three pieces as shown in the diagram. Okay, so this is a magnet. So it has faced the north and then the south. So when it is broken, this one usually becomes the south, then this one usually will be the north, then the south, then here it will be, this is the south, this will be the north. So when they say what will be the polarity of the ends labeled E, F, G, and H, I've already put here. So E, it is the south, okay? Then F, here it is north. Then G, here it is south, okay? Then H is north. So the answer is B. A polythene rod can be charged negatively by rubbing with a woolen cloth. How does the woolen gain its charge? A polythene rod can be charged negatively by rubbing with a woolen cloth. How does the rod or gain its charge? By gaining electrons. Yeah, it gains electrons. Oh, in fact, this one, it's here by gaining. What have I said? Proton. This is actually wrong. So the full question is here. So by gaining electrons, D, gaining electrons. Then this one, the diagram below shows a circuit. So this is a circuit. This is a 3 volt, 3, 9 here, resistor. We have 12 here, 6. Here voltage we don't know. Here voltage we know it's 6. Then they say what is the reading of voltage V2? Oh, this will be simple. Like V3, they've told us V3, which is total voltage, is going to be supposed to be V2 here, V1 I mean here, plus this V2 here. Now V3 it is 9, so we'll put 9 there equals V1 here it is 6, then plus V2 is what we are supposed to know. So it will be V2. So we'll cross collect like terms. This will go this side. 9 minus 6 is going to be V2. So V2 is going to be 9 minus 6, it will be 3. So it will be 3 volts like this. Then we come here. If the electrical energy costs that per unit, what is the cost of running that? This is, I've already solved such a question. I'll skip it. Then why is soft iron used in the core of a coil direct current? This one I also already stated. Then this one, I already answered the question like this. So I already answered the question like this. Okay, let me try to answer this one. Figure B8.1 below shows a circuit diagram with a lamp connected to a 12-volt battery. Okay, so this is a 12-volt battery, current 0.5, a lamp there. Calculate the charge passing through the battery in 2 minutes. Okay, so calculate the charge. So you know current is equal to charge over time. Then formula, charge is going to be equal to current times time. Then current they've given us 0.5. Now time is in minutes, so convert these 2 minutes into seconds. It is going to be 60. So it is times not 60, 120. is going to be 120 seconds. 120 seconds, this time converted into seconds, 120. So what we are going to do quickly, we are going to say 0.5 times 120 to be 60. So charge will be 60 coulomb. So you put 60 coulomb. You come here, how much energy is transferred by the battery? So remember, energy, I told you that energy can be equal to also power times time, but it can also be equal to like a volt. For example, volt is equal to energy over charge, meaning energy can also be equal to volt times charge. Yeah, so this is the one I'm going to use. So energy is going to be equal to voltage times charge, and voltage here is already provided, which is 12, and we put 12 times charge, we found it to be 60. So if we multiply 12 times 60, 12 times 60, 12 times 60, it's going to be 720. So 720 joules. So here you write 720 joules. Then here they're saying calculate the resistance of the lamp. So resistance of the lamp will be simple. We have current and voltage. Now resistance. So resistance R is going to be voltage over current. Voltage is 12 divided by current is 0.5, which is going to be, we'll do it quickly, 12 divided by 0.5, it will be like 24. So it will be 24 ohms. So you write 24 ohms. We move. Okay, so here they're saying figure 7.1 shows a transformer with 200 turns on the primary coil connected to a 12 120 volt AC main supply used to operate a device labeled 240 to 120 watts. So this is 200 turns, this is and 120 volts. So then this side is 240 volt, and this is 120 watts device. Then they're saying what type of transformer is shown in the figure. So if this side you have little coils, like here there are little coils, right? Here there are more coils. So this is a step up transformer. So you say this is a step up transformer. Explain briefly how a transformer works. I'm just going to just say, like what I explained the other one, like alternating current passing through the primary coil induces the changing magnetic field into the iron core, and the changing magnetic field in the iron core induces alternating current in the secondary coil. Okay, let me repeat. Alternating current in the primary coil induces changing magnetic field in the iron core. This is the iron core. Then a changing magnetic field in the iron core induces alternating current in the secondary coil. That's the explanation here. We move. Then here they're saying calculate the current passing through the primary coil considering the transformer is 100% efficient. This one we have already done. This one also we have already done. So let me come to this one here. Between B, calculate the resistance between AC. Calculate the resistance. So figure B, figure 8.1 shows an electric circuit diagram. Okay, we have 2. This should be, what is this? This should be 3.5, guys. It's not clear. 3.5 volt. This is 6 volt. This is 4 volt. Okay, so this is 6 ohms. I mean, this is 4 ohms. This should be 3.5 ohms. Then when they say calculate the resistance between A and C, between A and C, so they want this. So first of all, find this one, then you add it to that. So resistance in parallel here, it is going to be 4 times 6, then over 4 plus 6. So it is going to be 4 times 6, like 24, divided by like 4 plus 6, which will be like what? 10. So 24 divided by 10, 2.4. So now plus now this 3.5, which is going to be like 5.9 ohms. So it will be 5.9 ohms. So I've added this one to what I found here, which is what I found here. This added to that to find the resistance between this point and that. Then they're saying calculate the potential difference across the 6 ohm resistor. So the potential difference across the 6 ohm resistor here, 6 ohm resistor here, it is the same here. So they want the potential difference here. So that one is just the same like I told you earlier on. Now, the problem is we don't know current yet. So first of all, we need to know current. So current is going to be equal to voltage divided by total resistor. So voltage, we are told it is 24. So total resistor is 5.9 if I didn't make a mistake here. So you divide 24 divided by 5.9. Let me first confirm. 4 times 6 equals 6 times 4, because here divided by 10, 2.4 here, plus 3.5, 5.9 here. So 24 divided by 5.9 equals, so it is giving me like 4.06. So that is the current. 4, okay, let me just assume that it is just 4 amps. Then, but what we are interested in is the voltage here. So voltage here is going to be this resistor we found here, which is 5.9. Then it should be now times the current, which is 4 here. So which is going to be equal to, so what I'm going to do is to get this current, which is on my calculator, this one, times 5.9, so that this is not making sense now. I'm getting the same value. Shouldn't be 24. Where have I gone wrong? Voltage here. Oh, okay, yeah, let me see. I want to find the voltage here, but first of all, I need to know the total current. So total current is going to be what? Total current, I found it to be voltage divided by 24 over 5 point. Oh, sorry. This is an error that I've made. I've realized. So here, I want voltage here. So since I'm looking for voltage here, I'm saying voltage, I've seen the error I made. Voltage is going to be current times resistor. So is equal to current, we said it is 4 times now total resistor here just on this part was 2.4. So 2.4. Yeah. So now that way I'm going to find the correct answer. So let me do like this. I want first to use that current 24 divided by 5.9. I'm here. I want to use this current here times now 2.4. So times, this is the current times 2.4, 2.4. This resistor here, which is this one here, which is 9.676. So it will be 9.76 volts. So this is the voltage here, so 9.76 volts. So the voltage across this ohm resistor is the same across these points. So it's the one here. And when you come here, we are done. So this, I think this is simple. We already found a question like this. Okay, now we come to this one maybe. Here the same figure B3.1 shows some energy conversion in a coal-powered station. So this is a coal-powered station, so study it carefully. So here you have 1000 joules of energy of coal in coal. So this energy is put into a boiler turbine generator. So out of that energy, 70 joules wasted in friction inside the boiler here. Then some of it energy is wasted energy goes like that. In cooling tower here, energy is lost there. Then from there it goes to 30 joules energy wasted in heating wires here in a transformer, then connected to the tower. Then 300 joules of electricity goes into a supply. Then they say how much useful electrical energy is provided by the power station. How much useful electrical energy is provided by the power station? So you just get that one. It is the one that went out into the power line. So the one which was used in the power line, it's the useful electrical energy. So there we are just picking and putting. Then here they're saying calculate how much energy is wasted from the cooling tower. So here cooling tower, we need to know energy wasted. So wasted. So here we are going to have energy that came in is equal to all this energy here, energy here, energy here, and energy there. So we are going to say the input energy here, you are going to use like input energy must be equal to output energy. Input energy was look at me, input energy was 1000, okay, which was in the core. It was 1000, like here it was 1000 joules. So it is the one went to output. There are so many energies on the output. There's 70 plus this one we don't know, we'll give it x, then 30 and 300. So this one went into 70 plus x plus 30 plus 300. Okay, let me see if I'm correct. Yeah. So here we are going to say 1000 is going to be equal to, we'll add this plus this 300, it will be like 330 plus 70, it will be like 400. So we'll have like 400 plus x, the energy wasted. So we'll correct like terms, will be like 1000 minus this 400. This side will be like x. So it will be like x is going to be 1000 minus 400 would be like 600 joules. So this is the energy which was wasted, like 600 joules. Then they say, see, calculate the efficiency of the power station in the production of electrical energy. So efficiency is given by energy. Okay, efficiency, that is efficiency formula. So efficiency is given by efficiency is equal to energy output over energy input. Oh, let me not confuse here a lot. It's going to be equal to energy, energy. So I'll put U here over input energy. That's what efficiency is. Then times 100%. So it will be useful energy, useful energy over input energy. So equals useful energy is the one that went there. The useful energy, which is 300. So we'll come and put 300 here, joules over input energy was what was there. Input energy, what was put into the whole power supply machine. So it will be 1000, okay, then times 100%. So this one and that one will go, that one and that one will go. 1 into 30, it will mean that we have 30% efficient. So that's the answer, 30%. Then we'll come to this one here. This one I think is simple. I want to see some other questions here. Yeah, like a cell phone charger has a transformer of 200 turns in the primary coil, which converts 240 volts AC to 6 volt AC, and a rectifier that converts 6 volt AC to 6 volt DC. So what do the letters AC and DC stand for? Remember I told you this comes, AC comes for alternating, this is a alternating current. Then DC stands for direct current. Then how many, okay, this you already know how to solve. A small heater operates at 12 volts, then 2 amps. How much energy will it use when it is switched on for 5 minutes? So remember, energy has got this formula. Energy is equal to current times voltage times time. So you just use this to calculate there. The diagram below shows magnetic field, but this one you should change it in 2 seconds. So the diagram below shows a magnetic field between north and south poles of magnets. The diagram below shows some questions are not well phrased. The diagram below shows magnetic or field. The diagram below shows magnetic field between the north and south poles of magnets. Okay, north and south. Okay, let's see the question. Which numbered diagram shows the correct magnetic field pattern? So if you have a north and the south, it should be like this. Magnetic field should move from north to south like that, not like this, not like this here, or like this. So 4. So here when they say which numbered diagram show the correct magnetic field pattern, it's 4. How many turns are this one already covered? This one already, guys, don't worry. So there was someone sent a question like this one, I think, to be assisted. So figure B7.1 shows a circuit diagram connected to a 12-volt supply. Okay. Then they're saying calculate a combined resistance of 2 ohm and 6 ohm. So of 2 ohm and 6 ohm. Yeah. So here you need to study it carefully. So this diagram, when you see here, this switch is not connected. When the switch is connected, then the combined resistor between the 2 ohm and this one will be like in series with this. Okay, let me try to put like this is the 2 ohm resistor, then let's say it is going like this. So this is the 3 ohm resistor, then this is the 6 ohm resistor like this if it is completely connected. So this resistor is in series with this. So if they say combined resistor between the 2 ohm and the 6 ohm, they will be in series with each other, not in parallel. So you add this plus this. So you just say the combined resistor, which is total, is going to be the 2 ohms plus the 6 ohms, then which is going to be just 80 ohms. So here you put 80 ohms. Then we move. Here they are saying total resistance in the circuit when the switch is closed. So what will be the total resistor when the switch is closed, meaning the total resistor here? So first of all, you deal with this, then you add this. So this one is in parallel. So this one which is in parallel, first you deal with it. The one in parallel resistor is going to be like 3 times 6 over like 3 plus 6, which is going to be like 3 times 6, which will be like 18, divided by 3 plus 6, it will be like 9. So this will be like 2. Now you add this other one here, this other 2 here. So plus now 2, it is going to be 4. So here you put 4 ohms. Then here potential difference across the 2 ohm resistor. So potential difference across the 2 ohm resistor, this one here. So for you to know potential difference, first of all, you need to know total current. So let's calculate total current first. So total current is going to be equal to total voltage over total resistor. So total voltage, if you come here, total voltage is 12. So you put 12 here over total resistor here, the one you found here, total resistance is 4. So divided by 4. So 4 into 12, it will be 3. So that is the total current 3. Now, they want potential difference across the resistor 2 ohm resistor. So now we know current that is flowing here, it is 3 amps. So now the current is 3 amps. So we use that current passing here and this resistor to find the total voltage. So total voltage is there, it will be current times total resistor plus resistance. So total current is 3 and the resistor itself is 2 here. So you multiply here to be 6 volts there. So here you write 6 volts. Then they're saying the total current flowing in the circuit when the switch is closed, or total current we have already found here. It is 3 amps. You show them how to calculate it if they want. Over R, then you say 12 over 4, which is going to be 3 amps. Then you continue. Okay, let me see the side. Okay. Figure B8.1 shows a diagram of an iron core electromagnet. Okay, so the iron core electromagnet here state 2 ways in which the strength of the electromagnet in figure B8.1 can be increased. Okay, so one, by increasing the turns, by increasing the turns. Two, by increasing the voltage, by increasing the voltage. So then explain why the core of the electromagnet is made of iron instead of steel. I already explained such a situation. So these I've already dealt with it. So let me answer this one. Which of the following materials would be most suitable for constructing the core of an electromagnet? It should be iron here. This one I already answered the question like this one. Then this one also, it's simple, guys. Okay, let me just see which one I can try to answer. Okay, some of these they're already on my channel, so these ones. Okay, let me try to calculate this one. Figure B8.1 below shows 2 pairs of 3.0 amps resistors connected to a that. So we have these. Then they're saying calculate resistance in the circuit between P and M and N. So M and N, the resistors, first add these. So 3 plus 3 here to be like 6. Even if 3 plus 3 is 6. So you have like 2 now here, 1 and this one in parallel. So this one, they're in parallel. Total resistor will be like 6 times 6 over 6 plus 6, which will be like 6 times 6, it will be like 36, divided by 6 plus 6, like 12. So 12 into 36, it will be like 3 ohms. So that will be the total resistor, 3 ohms. Then you come here, current through the battery. Current through the battery will be current is equal to voltage over total resistor. So voltage is what? Voltage is 6, then a resistor is 3. So 6. So 6, 3. So 3 into 6, 2. So current, it will be 2 amps. Then power developed in the battery. Power is equal to current times voltage. So current, we know that it is 2 times voltage is 6. So you multiply, it will be like 12 watts. So you say 12 watts. Let me see other current, other. These are simple, guys. These are simple. This one, like the one, it repeated itself. So this one, it repeated. This one, 300 joules. This one, 600, I think. I calculated 600 joules. This one, 30%. I still remember. Then this one, what is the maximum current through the conductor? So the maximum, this side current, this side voltage. So the maximum current is somewhere here. Here, right? So the maximum current should be 3 amps here, where this one ends here, because it is going, then it stops there. Then here they're saying calculate the resistance of the conductor when the current was 1. So when the current is 1, it's 1 here, you come here, you need to know what voltage is going to be. Current 1, voltage is going to be 1 also here. When current is 1, we see that voltage is 1 also here. So now you say resistor is equal to voltage over current. Now voltage is 1, current is 1, so resistor is also 1. So 1 ohms. Then calculate the power in the conductor when the voltage was at 6. So power is equal to voltage times current. Then you come here, when voltage is 6, the current should be 3. So you substitute here, voltage is 6, current is 3. So this would be 18 watts. So 18 watts. So we go to these are simple, guys. These are simple. Okay, I'll come to this one here. Which graph shows the voltage output V against time for an AC generator? An AC generator produces a voltage which is like this. This is for AC like this. This is for a DC with a rectifier, I think. This one with a DC without a rectifier. This one is the voltage output of a battery. Then we move. Then here they're saying explain what is meant by magnetic field. I say this is the region. This is the region around a magnet where the force of attraction is experienced, or magnetic force is experienced. Then electric field. This is a region around a charged particle. It's a region around a charge where the force of attraction is experienced. Okay, complete the diagram to show the pattern and the direction of magnetic field lines in the space around the bar magnet. Okay, so this one, if it's a magnet, the field will be like this. Okay, so from north to south, arrows like that. Okay, shows a positive charge sphere near to an initially. I think this is already known. This will be like negative, this will be positive. Okay, this is simple, guys. These are simple things. Okay, all these are simple. We have already almost the same. Okay, so which diagram shows the graph of electricity generator? So this generator here, it is a DC generator. The following diagram shows a device that is used to generate electricity. So the one which has a commutator like this one, it is a DC generator. So if there's a which diagram shows the graph of electricity generated, So in a DC generator, DC generator will produce like this, but this one is like with a rectifier. Okay, so between this one and this one, but the correct one should be this one here. So here now I already answered this this is the same. So these are simple, guys. So let me end here so that I will be able to now look prepare myself for atomic structure, electronics, and the radioactivity. Also, I'll pick just a few important topics because time is not with us. Okay, so for now we end here. Bye, see you in the other video.